Okay, grade nines, until things return to normal, this is how we're going to be doing the rest of our electricity unit, at least, I would think, which is going to take us probably 2 more weeks from now. It says March 28th up in the corner. That's because that's the date that I'm making this, but I'm trying to get it to post, I think, for April 6th. I said you only had to do those 2 sections out of the textbook over those first 2 weeks. Hopefully you're done those and have handed that all in. If not, get caught up quickly because I'm starting to mark that. So that stuff was meant to be easy stuff you could do on your own, stuff that you could just kind of read and do. I don't think you could do Kirchoffs laws for circuits on your own. It's not that it's that complicated, but it helps to have an explanation and some drawings to go with it. So there's 2 rules. There's a voltage rule and there's a current rule. We are starting with the voltage rule. So in a circuit, for any complete loop, complete path in a circuit, the sum of the voltage gains in the sources is equal to the sum of the voltage drops in the loads. As follows, the trucks must return empty. So an old textbook I used to use visualized the coulombs of charge traveling around the circuit as being full of energy. Okay. And in each load that they passed, they dropped off some of that energy. So if you gain an amount of voltage in the source, because that's what the source's job is to do, is to give the charges energy, joules, volts, and you drop some of that off here, some off at V2 and some off at V3, then you have dropped off all of that voltage. So the total voltage gained in the source in a simple series circuit like this is equal to the sum of the voltage drops in the loads. So this was a voltage gain in the source, and these are all voltage drops. Sum of the voltage gain has to equal the sum of the voltage drops. First and easiest example I can give you is something like this. So each coulomb of charge as it passes through the source gains 9 volts of potential difference of energy, let's say. And they come around and they come around and they drop 3 volts off at V2. How many volts must they have dropped at V1? Say it to yourself, say it out loud, say it in your head, whatever you got to do. If your brain came up with it must drop off 6 volts, then you were correct and you understand Kirchhoff's voltage loop rule. The voltage drops, 3 and 6, had to equal the voltage gain. The trucks had to return empty. With a parallel circuit, some people will say it's more complicated, some people will say it's easier. So in this case, it doesn't tell you how much voltage they pick up at the source, but we know they pick up their voltage at the source. So they go through the source, they pick up a number of volts. I know I've only got 2 cells drawn there, which some of you would say, well, that's a 3-volt gain. But we're just always drawing 2 cells, and we're just going to put in whatever voltage we want. So they gain an amount of voltage, and they come along, and they come along, and they go through V2, and then they come back to the source. That's a path, right? For any one complete loop, complete path. Well, there's a complete loop. There's a complete path. So in that complete path, they dropped off just 6 volts because they only hit one resistor, one load. So how many volts did they have to gain at the source to make the rule work? And if you said 6 volts, you were correct. Now, if I can, I don't know what I've done now. There we go. If I can change my pen color to, I don't know what's going to show up nice on this. Let's check yellow. Oh, it actually looks pretty good. The reason I'm doing that is I just want to show you, well, what happens if we know now that they gain 6 volts at the source? That's fixed. That can't be changed. So now let's take a different path. We know they gain 6 volts at the source, but now what about the coulombs of charge that don't go through that V2, that load on the end? What about the ones that go through there? Well, if they gain 6 volts at the source, how many volts do they have to drop off at that one resistor that they hit? The answer, 6 volts. That's all there is to it. So in a straight parallel circuit, I really want you to understand how they work, but what if we added another resistor here? How many volts would drop off at that resistor? 6 volts. If I kept adding more and more resistors in parallel, they're getting pretty ugly there at the end, they would keep dropping 6 volts because there is only one load that those coulombs would hit in each of those pathways. So that was a series circuit followed by a parallel circuit. Now this is called a combination circuit. Now it's called a combination circuit because some of it's in parallel and some of it's in series. And that can make it, well, this is as tricky as it's going to get. I'll just tell you that right off the bat. So the goal here is to fill out all the voltages. So you've got to figure out what V4 is, and you got to figure out what V2 is. The other ones are given to you. So just like before, it picks up 12 volts at the source. It doesn't matter which path you pick. I'm going to take the far path first. I don't know why. No particular reason. And this is exactly what I do even after all these years of solving these. I either just put my finger along the path, or I draw it in with a pencil or a red pen. And I think about, okay, so if it gained 12 volts at the source, it had to drop some of those 12 volts here, some here, and some here. Well, it tells me that it drops 6 volts off at V3, 3 volts off at V1. So how much voltage did it have to drop off at V4? If you were thinking that it was another 3 volts, then you were correct. Let me double check. Does 3 volt drop, 6 volt drop, and 3 volt drop add up to a voltage gain of 12? If yes, then I've done it correctly. So I'm going to erase that pathway. And now I'm going to take the near path through V2. Again, it picks up 12 volts at the source, and now we're going this way. If it drops 3 volts at V1, because now it's got to go through V1, but it gets to skip V3 and V4 and just cut through V2, how many volts did it have to drop at V2 if it follows that pathway? I'll pause for a second here. If your brain came up with 9 volts, then you are correct and you understand how to use Kirchoffs voltage rule for combination circuits, the most difficult circuits we're going to tackle. Let me double check. 9 volt drop, 3 volt drop. Does that add up to a 12 volt gain? Yes, it does. And we're ready to move on to another combination circuit. So this one can be hard for some people. I feel like I'm switching back to red here. Let's see how that looks. Yeah, that looks good. We know that it picks up some voltage at the source. We don't know how much though. So then you might think, all right, well, I can figure it out by figuring out the drop. So it drops 6 volts off there. And then we get to this. That's called a junction point where the coulombs can split off. And if I want to figure out what this VT is, the total voltage, then I want to go along the path where I know all the voltage drops. So I'm going to take that path right there. Because now I know if I take that path, it drops 6 volts, 2 volts, and 1.5 volts. So if I take that path and it drops off those 3 voltages, how much did it have to gain at the source? 6 plus 2 is 8, plus 1.5 is 9.5 volts. Now, if you follow the other pathway, if I take those off, if instead I drop 6, and I want to figure out that unknown drop, 9.5 volt gain at the source, we can't change that. It drops off 6 here, 1.5 here. How much did it have to drop at V2? And you'll find that it's 2.0 volts. Now, some of your brains would be telling you correctly, oh, I think I see something here, that these 2 resistors were just in parallel with each other. Does that mean that 2 resistors in parallel are always going to have the same voltage drop? And yeah, that's true. Be careful with it, because although these are 2 and 2, if I was to add another resistor here, then they wouldn't be 2 and 2. It would be, they'd have to add up to 2 and 2, but that would mess up your logic there. But again, we're not going to get any harder than these combination circuits. So that is a rule that you can think about as you're doing these. So the only other thing to learn for today and tomorrow, that's Monday and Tuesday, is the current junction rule. Now I mentioned really quickly what a junction was, and I'll try and show it to you again. So what a junction is, at a junction in a circuit, the current entering must be equal to the sum of the current leaving the junction. The dump trucks cannot leave the road. If you like that trucks analogy, I'll show you what to do here. So forget about the energy they drop off. Now just think about the number of coulombs, the number of dump trucks, or current, if you recall, is the number of amps. So if we have a number of amps enter this junction, by the way, this right here is a junction. How do I spell junction? So some of those trucks, those coulombs, those amps can go straight ahead through I1, and some of them will go down through I2. So what the rule is that the number of charges, the number of amps entering that junction has to equal the number leaving the junction. In other words, IT has to equal the sum of I1 and I2. And you don't even have to write down this part, but I'm just to give you an example. If 10 amps of current enter that junction and 2 amps go straight ahead, how many amps must have went down through I2? 8 amps. Because again, the coulombs, the current, the trucks cannot leave the road. So if 10 trucks get to this stop sign right here and 2 amps go straight, 8 amps must have turned right and went down through I2, right? That's the current rule. If you understand that, then you understand the current rule. Let's apply it to some examples. So if 1 amp of current leaves the source, how many amps get through I2? How many amps get through I1? Now think to yourself, the first thing I usually ask a class if I'm doing a live show here is that I say, what do you think's the most common wrong answer that I get on a question like this? By far, the most common wrong answer I get is, oh, I know what to do. It's 0.5 and 0.5, right? That is wrong. That is wrong. That's by far the most common wrong answer I get. The rule is the current cannot leave the road. And if you think of it as trucks or people or coulombs, if you understand coulombs, if one of them is walking along this pathway, then how many are going to get through this? One of them is going to get through this. How many of them are going to go through this one? One of them. We're not dropping off amps. All you can do is split them up if there are multiple pathways, and there's only one path, so it's all going to be 1 amp. If I had another resistor here, it would also be 1 amp. 1 amp all the way around that path. So now we're going to go straight to a combination circuit. You might recognize this setup from the voltage loop rule. In this circuit, we have 2 junctions, one there, one there. 3 amps leave the source. Obviously you guys want to pause this video so that you can draw these into your notes. I'm going way too fast for you to keep up without pausing the video. So pause it every so often, write it down. It may even be useful to test yourself and see if you can figure out what the amperages are before you hit continue on the video. So anyways, 3 amps leave the source, 3 amps, 3 amps, 3 amps, 3 amps, 3 amps get to that point right there. Some of those 3 amps go around the long way, and some of those 3 amps go straight up through this way. This 2 amps over here is significant, because that's telling me that 2 amps went that way. That means that 2 amps go through I3. Now I'm going to pause here for just maybe a 5 count in my head. If 2 amps took the long path, how many amps took the shortcut and went through I2? If your brain gave you 1 amp, then you are correct. 3 amps got to the junction. If 2 amps took the long way, then 1 amp must have took the shortcut and got back to here. Now this is another junction. How many amps go through I1? Well, now you've got a combination. You have 2 amps that came around the long way. 1 amp took the shortcut. However, they come back together, and you're going to get 3 amps once again when they join back up. So they split up into 1 and 2, took their separate paths, but then they got back together back to 3 amps. That's how you this is about the hardest case that you would have to deal with for the current rule. Here's another current rule. It looks like it gives you very, very little, doesn't it? It doesn't give me I1. It doesn't give me the total amps. It doesn't give me the I4. But it gives you enough. I'm always going to give you enough. All right, right here. This is all I need because I've got 3.5 amps coming from I2. I've got 1.5 amps coming from I3. So how many amps join up and go through I1? Well, all you got to do is put them together. 3.5 and 1.5 adds up to 5 amps. All right, 5 amps, fair enough. So that means how many amps go through the source and how many amps go through I4? Well, there's no place for them to split back up before they get to IT, so it's going to be 5 amps. It's going to be 5 amps. That's it. That is how the current rule works. Is that all I have? That is all I have. Can I write on this screen? I can't. I'm going to keep my annotations here and just continue to talk. So I've got 2 practice sheets posted. I think I'm going to do my own answers and post them maybe the second day of this. So I'm planning on that being the Tuesday. So I want you just to compare your answers. I want you to take those practice sheets, draw the circuits, or print them. It'd be great if you can print them, but if you don't have access to a printer, just draw them. It's not a big deal. And test yourself. Try them all. Compare them with what I get. Compare them with each other if you'd like to, if you have the means to do so. And if you get all of them right, or very close to all of them right, I would consider you experts in using Kirchoffs voltage rule and Kirchoffs current rule. All right. If you do just one of those practice sheets today, let's say you do the voltage loop rule one today, and then do the current rule one tomorrow, then that'll be just fine. I'm not going to post anything new other than maybe the answers to these questions tomorrow. I think that there's a video also posted with this, a continuation of that kind of history of electricity and electricians. So you can watch that at your leisure. I was going to show you parts of that in class. If you're interested in that, then you can continue to watch that. If you're bored, stream it. It's just a YouTube link. Anyway, that's all for now. The rest of the unit is going to be done this way, and then I got to figure out what to give you as a final assessment for this. And it'll be in about 2 weeks' time. All right, that's all for now.